welcome Carlos Duarte. Right, thank you all for coming. And like Jake said, that I'm going to talk about my thesis, and my thesis is basically two parts. One of them is the occupancy part of analyzing sensors in a commercial office building, and the second part is the calibration process of trying to see what the schedules that I found out with the occupancy research, how they affect the energy modeling. So, but today I'm going to focus more on the calibration process and how to arrive to a calibrated model. And I would just like to take this opportunity to thank Marva and Mike for giving me information about their building, letting me use bugging them every time, and the Christian Corporation for letting me use the building. Well, the occupancy research, there was 625 sensors at the Banner Bank building, and these controlled the lighting. They when at least one person enters the space, it will just turn on the lights, and it doesn't count how many people there are. And so I had 2 years worth of data for all these 625 sensors, so it was a lot of data to process. It took a while and crashed my computer a few times, but I was able to get results out of it. So I broke it down into space types. So I individually took the sense, or determined the space type where the sensor was, and created these profiles. Like down here, all the different space types. This red one is the private offices, and it's fairly lower than the other ones where more people are there frequently, like more common areas like open office, lobbies, bathrooms, and stuff like that. So they resemble a lot like the ASHRAE occupancy schedules that are found in Standard 90.1 2004. And it's just like the only reference I was able to find when I started my research. There was it doesn't explain what kind of offices there is, like is it open offices, is it for private offices? But as you can see, there's quite a significant difference between what I found in my research and the ASHRAE reference, and it's about 47%. So
what's a diversity factor and how does that work?
So a diversity factor is a factor between a fraction between 0 and 1, which tries to take into account the variability of equipment in the energy simulation model. For example, in my research in scheduling, it's trying to vary the people that go into the building. You specify a maximum in the energy simulation model, for example, 800 people. At this point, 40% of that 800 people are inside their private offices, and about 80% of that people are in the open office space. So that's how diversity factor is just try to take in the variability of a database basis in the simulation model and get accurate results. So I further went into detail I focused on private offices, broke them up into month type over here, just to see if there was significant variance through the months. And as you can see, they're pretty close. So I broke them down into 3 categories with high, medium, and low occupancy profiles. It wasn't very much significant, or there was a statistically significant difference between them. But the second part of my research is trying to prove if they do a significant impact in the resulting energy use in the building. So I also did it for day types, and all these show like a deterministic diversity profile, but in reality, people behave randomly. They don't always show up at their workspace at the same time, or the same time, or leave at the same time, go to lunch and stuff like that. So this graph, I'm trying to show like the variability in people. And I'm just down here. People have done stochastic. They're trying to model human behavior in energy modeling. So I'm just comparing one of the researchers' model to the deterministic profiles that I came up with. So the second part of my research is more on the trying to figure out what's the impact on the energy use in the building versus using the three types of models, one from the ASHRAE, one from the research that I found from studying Banner Bank, and one from the already existing schedules and calibrated models done by our lab. So I did 3 reference buildings that are found on the DOE, the Department of Energy website. They have a small, medium, and large office buildings. So I did the analysis for those 3. I'm still working on the Banner Bank results, and I already done the schedule switch out on the calibrated models done by the lab. And reference buildings, they don't have space types where I can substitute all my profiles that I found out. They only have one kind of space, which is just a office space, and that is just generically input into the whole building. Whereas the calibrated models, they have more the modelers that initially developed the model of the simulate or the model define more space types. So I was able to incorporate more of my research into those types of buildings. And some of the space types that they had were private offices, open offices, conference rooms, break rooms, bathrooms, service rooms, and stuff like that. And one interesting thing that I found out through some of the preliminary switching out the schedules on the calibrated models and the reference is that as the building size increases, the dramatic or the delta in the end consumption of the building is not as drastic as I would see in the smaller buildings. So, for example, the small offices had almost a 50% change when I substituted the ASHRAE versus the measured, and the larger buildings had a 60% difference. So there might be a correlation there. So now to the focus of this presentation. What is calibration? So based on a Redding in his paper Literature Review on Calibration of Building Energy Simulation Programs, Uses, Problems, Procedures, Uncertainty, and Tools, he describes calibration as the process of using existing building simulation computer and tuning or calibrating the carries inputs to the program so that the observed energy use matches closely with the predicted of the simulation program. So why is this important? And that's another thing that I'm trying to get more sensitivity analysis in my thesis. But why is this calibration important? Well, previous studies have shown that uncalibrated models have been up to 30% off from the utility data and 90% off from the individual HVAC system components, fans, pumps, chillers, air handling units. And in this study, they proceeded to build a model in 2 levels. The first level was the maximum they could spend is 20 hours. They had no thermal mass, physically correct layouts and geometry, typical values of general observation for occupancy, equipment, lighting, and all the typical HVAC components were assumed to be default for the initial run. And the second level, they took another 20 minutes or 20 hours to define more specifically their buildings, and this including the thermal mass, site-specific values for occupancy, equipment, lighting, obtain detail surveys, as-built definition of the different HVAC systems. But what was interesting that as they defined more of their parameters, their uncertainty increased to the high 20s, the high 80s over here. So that's an interesting thing. And the graphs below, the pie charts over here, is based on my research. This is my first initial run of the calibration model with Banner Bank, and this is what I'm trying to calibrate it to. So there's a big work to be done in these. So, and once you get a calibrated model, you can do, the model will have more increased confidence of the model energy, so they can apply it to energy conservation measures and produce the same results as if they were implemented in the real building. So Jake is going to talk about more about the ECMs.
Actually, I want to mention one more thing about this slide in terms of, why is calibration important in terms of predictive energy modeling, right? So we've all heard the studies and the lawsuits against LEED, for instance, about do LEED buildings actually save energy. They took a lot of actual measured utility data from LEED buildings, tried to compare them against the energy models, and they tried to kind of raise this idea that, oh, well, it's not predicting, or it's not actually consuming as much energy as you predicted in your model. But, you can't really compare the two because the ASHRAE Appendix G protocol is not a predictive energy model like energy calibration. So there are two very different animals. So that comparison wasn't necessarily fair for them to be able to make some of those assumptions. So, this is something where we have to get into a much higher level of detail and investigation when we're starting to do some of these measures. And one, of course, is for the idea of being able to predict energy modeling, but the other is to have an investment-grade confidence when you're starting to upgrade and do these kind of deep renovation buildings, to where you need to know that if you invest in your building by X, that you're going to get X amount of savings, so you can actually come up with an investment plan and allocate capital and so on and so forth. So increased confidence in these ECMs is really critical, and it's how we really used it in the type of consultation projects that we've worked with at the lab. And so this graph just dictates one thing about the process of going to these this type of integrated design towards existing buildings. Of course, we're all familiar with the entire process, which starts off with benchmarking, meetings with the owner, your energy model, your design charrettes, all that stuff. But this is just kind of a microcosm, a blow-up of the kind of simulation portion of that integrated design process. So essentially, step one is arriving at a calibrated model from all your site visits and your 40-plus hours or however long it takes to come up with that. Step two is your adjusted baseline, and we'll talk a little bit more about that later, which would be representative of this bar here. And essentially, once you calibrate to your year, that might not necessarily be the actual baseline that you use moving forward that you compare energy towards. The biggest example of that would be if you're trying to calibrate a building that's 50% occupied. But when you're doing the investment analysis, you might want to know how much energy you're going to save if that building ramps back up to 90-95%, right? So you would do your calibrated baseline to a different condition, adjust it towards whatever baseline condition that you're doing, and then you're able to actually go through and test these different measures against. Another one that we'll see sometimes is a code baseline, depending upon what they're trying to look at, jurisdiction by jurisdiction, utility by utility. They might require savings to be predicted against what the actual code minimum would be. And in some cases, the buildings will actually consume more or less energy depending upon if they're code compliant or not. Fresh air is a big one. Are they getting fresh air? Are they not getting fresh air? There's a lot of different factors that can come into play. So another reason why calibration can be important is these models can really be diagnostic tools for trying to troubleshoot building problems or trying to understand how the building works in general. In a lot of cases, buildings are very complex creatures, and it's not always apparent, depending upon the amount of information that's available, to be able to actually model them. I mean, currently we're working on a hotel project where we have no plans to go off, zero. We have like maybe 25% of an architectural set, and that's it. So you actually have to do a lot of investigative work, and the model can start to help. So this example is of an office building that we worked on to where we didn't quite understand how the makeup air unit was operating. So we had heard different accounts from the building operations manager, from the HVAC technician, from the tenants themselves on how much fresh air was being admitted into the building, what the set point was for that fresh air. It was a makeup air unit, so it was providing fresh air to heat pumps, and what the schedule was. Do they run it all the time throughout the year? Do they run it in the summer but not in the winter, so on and so forth? And this yellow bar represents the variations between those different accounts that we got from interviewing the different components of what we're trying to get information for. And you can see that it has a huge difference on the overall target UI that we're trying to calibrate. So through this and through kind of some more investigative work, I believe we were able to arrive at this slice here, which was an on-off operation, so only being operated during the daytime with a set point of 65 with normal, I think, infiltration was layered onto that as well. So you can see that that's one of the processes that we can use to help diagnose buildings. Then, of course, one of the last reasons why calibration is important is for various incentive programs. Like Chris Paulo's custom efficiency program will actually pay the incentive based upon the amount of savings from a calibrated, deemed calibrated energy model. So this was just an example that I pulled off the website here. So you can go there to find out some more information. Chris actually is usually here at VSUGS, but he's not here today. This was interesting. So the model showed for this Grove lighting upgrade, around 800,000 kWh per year, and that multiplied by the 12 cents per kilowatt hour equaled a $95,000 incentive. And I believe the total project cost was 140. So they saved over 50%, just by having this model and being able to show savings from the calibrated model and submit that to Idaho Power for their incentive. So with that, I'll kick it back over to Carlos.
So how do you deem a calibrated model? There's currently two methods to arriving at a calibrated model. Currently in the ASHRAE guideline 14, one is the mean bias error, which if you take hourly data for the whole entire year, you can be in a tolerance within plus or minus 10%. And if you're using monthly data, you can be within a tolerance of 5%. And the M is measured utility data, S is simulated data, and then N is the number of data points you have. For example, in monthly, you will have 12 total points, and for hourly, you have 8,760. So you sum up all the difference between the measured and the simulated, and divided by the total measured, and that will give you your MB, your mean bias error. And I'm going to show examples for each after these few next slides. But another method found in the ASHRAE guideline 14 is also you can use hourly or monthly data, but the tolerance increases, and it increases because this one doesn't take into account because when you're measured. This doesn't take to account absolute errors. Like the measured and simulated can offset each other. So if you have a negative difference in one of the months and a positive difference in another month, then they can equal out to equal 0, and you have a mean bias error of 0%, which won't necessarily define the accuracy of the model. So that's why the ASHRAE guideline points to another method, which is called the coefficient of variance of the root mean square. And this one, you get the absolute value of the whole of the errors between the measured and simulated, square it, divided by the total number of data points, and sum them all to, you're going to get the square root, and divided by the average of the measured utility data. So it's more of a better measure of accuracy for the simulation results.
I just want to stop here for 1 second. Has anybody used these two equations to quote calibrated model before? And we just started using them recently as well. I hate these equations. Let's just get that on the table right now. And like Carlos said, the top one is essentially doesn't ding you as much for your monthly variation, and the bottom one does take that into account. But what we haven't found either in the literature review or in the actual ASHRAE guideline is which to use for which scenarios, right? So we have taken the stance lab, as long as we meet the criteria of one of these, then we can deem it calibrated, right? But we haven't really found a good protocol or reference to say you should use the coefficient of variation for root mean square error for these types of buildings or for these types of situations.
And another thing that the ASHRAE guideline doesn't state is where these measurements came from. Researchers think that when energy modeling started back in the 70s, that it was what the standard practice was to get these tolerances between 30% and 50% for the coefficient of variance and 10 and 5 for the mean bias error. So it's also unclear where these tolerances and these tolerances came from.
Yeah, because the tolerances should really be also based upon building type and potentially information available. He's trying to do a monthly calibration for a hotel. It's going to be a lot different than monthly calibration for a school versus an office building or something like that. So really, these are pretty blunt instruments to determine calibration. So another example for that is this is total energy. It doesn't really even take into account fuel splits, right? So we always impose as an additional requirement for the lab projects is that we're within about a 10% overall variance in the fuel splits as well, because that's really going to be what dictates the investment, right? Because you have to look at the price per unit of the utility cost. And so if you're off on electricity, which is more expensive, but not as off on gas, sometimes that can increase the amount of variance when you're looking at cost. So we use these as a guide, and we also layer in some of these other requirements that we feel are important to deem a model quote-unquote calibrated, and that has to deal with fuel splits.
So an example of the mean bias error is, so we took one of our utility data from one of the calibrated done by Jake, and the simulated results down on this column. So we take the utility data minus the simulated, get all the differences, and as you can see, there's some positive numbers, some negative numbers. So those set of numbers we're going to set each other, and to result into a negative result for the total errors. So you take that number divided by the total of this utility data, and you get a result of negative 1.4% for the mean bias error, and this will the model will be deemed calibrated. But we take the same data and apply the coefficient of variance for the root mean square. We see that the variance increases, but still the model is still deemed calibrated. So in this one, you take a little more steps. You first get the same error, square it, and then divide it by the total number of data points, which is 12 points for our case. So you get sum of all the differences between the utility and the measure and square root it, and then divide it by the average instead of the sum for the utility data. It's 30 for hourly and 15 for monthly. So it's still within the tolerance. But as you can see, it takes absolute values, which also increases the percentage by a lot, which is almost 9 times. A little bit more than that. So any questions on the methods?
I'm still happy with that number.
Still being calibrated.
Have you guys done any hourly calibration yet? We have not.
And that's usually because it's more difficult to get hourly utility data. It's basically more easily to find it just from the power bills monthly.
Well, we could, and then with the advanced metering infrastructure that's going on some of the buildings, that becomes a possibility now, especially by fuel time, so we can start to get even more accurate, with the new infrastructure.
So another resource for to deem a calibrated model is the MVP, which is the International Performance Measurement Verification Protocol, and it's option D, where it talks about how to arrive to a calibrated model, and it doesn't say specifics on what the tolerances may be. It just refers back to the ASHRAE guideline 14 with the mean bias error and the coefficient of variance. So, but it talks about like neat ways to arrive at discrepancies quickly just by line charts or pie charts breaking down the energy in use, and you want to try to model that as closely as possible, and which will increase the confidence in the predicted energy use. So here are some of the calibrated projects that Jake's going to talk about.
So this is kind of like our portfolio, right, just to show that we have had some experience with doing a variety of different projects. Some are direct consulting projects. Others are part of our EBR research. You might have heard of that. It's existing building renewal funded through NEA, and it's essentially trying to crack the issue of how to approach deep energy retrofits. We've done a couple of quote-unquote pilot projects where we've had to do calibrated models. But in general, we worked on the Jefferson Place building. It was built in 1913, very old building in terms of its systems. It was renovated in 1984, and we had utility data in 2008. So even that makes it hard to calibrate, just those 3 lines of information about the building. But we did a slew of different energy efficiency upgrades, including envelope and mostly with their zonal heat pump system. So that was, I think, the first project that we did. Ari and Hershana worked on that back in 2008, 2009 probably. The next one that we did was the Idaho office building, the Marsh and Sedgwick Center downtown. It was built in 2002, so a relatively much newer building. Same HVAC system, though, as a zonal heat pump on the geothermal system. So in this case, we calibrated to 2006 data because of its occupancy rates. We're trying to avoid a major equipment upgrade that they did to the cooling tower that there wasn't much documentation on. And we also did multiple staging packages for that as well. We did like an Entry Star version and then a deeper 35% overall version. But it was definitely a much different experience than trying to calibrate the 1913 building in terms of the amount of information that was available, how we got that info. We also did Capitol Gateway Plaza. It was built in 1999. It was part of our EBR research. It was pretty similar as well. And then we're also working currently on a Montana office building. It's a VAV system, 30,000 square feet. And it was actually built in 1956. And it's great looking at all these hand-drawn blueprints of the buildings to try to get information on. Interesting to me as an architect. And then currently we're working on a Boise hotel, 300,000 square feet, built in the 1970s. Like I mentioned, very little drawings to go off of. And it's like trying to model and calibrate 8 different buildings because of how varied the usages are. There's restaurants, there's guest rooms, there's a residential component, there's meeting rooms, there's all sorts of different things that are trying to go into that particular model. Then, of course, the Vanderbank building, which Carlos will talk about.
So, yeah. So the next few steps is just the steps I took to arrive at or in progress of getting a calibrated model of the Vanderbank building. So I'm just going to start with general and get into the details of more granularly. So the first thing is to just collect building level information. This includes site info, weather files, and utility data to calibrate. It's important to choose what year you want to calibrate it to, because if the building has retrofits that are not well documented, then it's going to affect your calibration as well, because it'll be hard to model specific. For example, right now I'm trying to model a recovery system in the Vanderbank building, because they have a neat setup in there for their water loop and their heating purposes. But besides that, you try to avoid those retrofits because it would make it easier. And another thing is that you want to take a year where the building has at least above 60% occupant. The occupancy exceeds 60% of the building, because that way the HVAC systems will be used more frequently. All the troubleshooting will be taken away, and they'll be more predictable. So type of constructions, walls, windows, you can able to get that from the architectural plans. And for window specifics, there's calculators out there that help a lot to get the actual the solar heat gain of the window, the transmittance, the reflectance, and stuff like that. So that's what I use to calculate the specifics for Vanderbank building.
It's amazing how difficult window specs can be defined on some of these projects. I believe on the Idaho building, we had to go all the way back to the mechanical engineers' HVAC calculations to figure out what the U-value SHDC were. They're not looking up the plans. Rarely they're in the submittals. So it's something that's always kind of a difficult thing to do. So we've come up with a protocol sheet that have a lot of different basic performance thresholds of different types of windows that we gathered from different research sources. So
one way to get around that.
Another thing is to simplify much stuff that you can, because it will reduce simulation time and resources spent. For example, the Banner Bank has spandrel in between in the middle of the facades, and some details of walls that are different than other sections of the exterior facade. And I just took the weighted average of all that and applied it uniformly throughout the facade. I did that for each of the 4 facades and got an average value, an average R value for each of the wall sections, and each of the AU value for each of the window sections. So this is where I was talking about getting to calibrate to a year that wasn't going to be too radical of energy consumption. For example, over here, this is where a lot of their some of their system improvements occurred. So it would be just difficult to model in the simulation to be able to input that into the model. So I chose to do 2008, and that was just the beginning of where I believe it's the beginning where they tried to do the heat recovery system. Is that right, Marv or Mike? The controls. So yeah, and as you can see, after they put it in the controls, there was a reduction in energy use. So that's my target, the dark red line for the electricity and the dark purple line for the gas consumption. So on the floor level, you want to figure out which systems serve each of the floors in the building. For example, which air handling unit, boiler, chiller serve each room. In my case, there was only one chiller, one cold water loop, geothermal with a backup, hot water for the hot water loop, and there was one air handling unit per floor. So and a lot of this I was able to determine from the energy management system of the building, and by talking to Mike, the building manager at the Banner Bank building. He was a lot of use, and a lot of the specifications you can get it from mechanical plants as well. And the floor layouts, you want to get as much information from the architectural plans, like sizes of the spaces, the geometry, and you want to also to aggregate these spaces. For example, I could have done my simulation model just the way I show it here on the floor plan, but I wanted to go more granular, because just in case the IDL wants to do more, use the energy model to do more research on it, or develop new algorithms for things like, for example, Chris is doing a blind controls algorithm for other buildings. So the result was 665 spaces for the entire building, with 502 thermal zones, which adds a lot of time to the simulation, which takes about 1 hour and 45 minutes just to simulate the annual consumption of the energy in this building. So, but just in general, just try to aggregate the space types as much as possible and reduce the complexity of the building. And thermostat settings, building managers can give you insight on what kind of set points they have at each floor. In smaller buildings, you can probably talk to the tenant to check out the individual thermostats. But I was able to get set points from the energy management system as well, and took an average for the whole floor, because defining 665 thermal set points for the entire building was going to be time consuming, and there's no relative easy way to do it in a simulation software.
Can I ask a question?
Yes.
On that floor plan that you're showing us, a really unique floor plan.
Yeah.
So my question is, were there, I'll just call it possible prototypical floor plans? So is there another one that is, further off? So
There was different types of floor plans in a Banner Bank building. I just took one of the meeting floor. I think this is 2. This floor plan 2, but other ones, like for example, the 11th floor is surrounded by office spaces, and another floor is just pure open space for the entire floor. So it just really depends.
Yeah,
And
I was wondering if there's, anything that you could learn and take away and then be able to use, on your building based on, there's so much information there.
yeah, and that's one of the things of my occupancy research. My first part of the thesis is to get what the occupancy schedules are for each floor plan. For example, the purple is open space, green is private offices, and just how it varies throughout the year. So yeah, that's a really good question. So as you get more granular, you get it more at the zone level, and that's where you define the schedules for the people, lighting, and equipment. You want to do fixture counts with the corresponding bulb wattages and ballast efficiency, because all these add consume energy, but also add heat gains to the system, which to the space, which needs to be compensated by the HVAC system. So for the equipment, also just do surveys of monitors, computers, which is the most common thing, and usually you arrive at the watts per meter or watts per feet number that you can put into the energy software. And ventilation requirements is a big thing also in the energy simulation. It can also deviate your results if they're not correct. They're not the correct ones. And as well for the infiltration zone is you gotta define which zones are exterior zones and define a infiltration rate for those zones, which can hugely impact the energy consumption in the building or the simulation model. And system levels, get specifications of cooling towers, chillers, air handling units, boilers, and the months of operation, any control sequences, because that's a big thing as well. When the HVAC operates, when it doesn't, and the efficiency and power requirements of each system. I use my phone a lot to just take pictures of the tags of the equipment just to reference them later, and that's a really good way to get them quickly looking up afterwards. So as you get into the system, and the system there has various components: pumps, fans, variable air boxes as well. Get these specifications, any resets of the systems, any setbacks, control sequences, and a lot of this information I was able to get from the energy management system as well, but a lot in detail from the building manager. He took me on a tour through the HVAC systems in the building, and I was able to understand how they operate and how they operate and how they connect to each other. So it's a good way just to visualize what's going on in your calibrated building. So documenting is important. You want to, for troubleshooting purposes, because initially your first iteration is not going to work out the way as you plan. There's going to be a big discrepancy. So you want to define the sources of information, document them, and researchers have suggested a data hierarchy where data log measurements is first priority, direct observation and interviews second, data obtained from benchmark studies is third, and the fourth standards, and the fifth information from the initial model if there's a initial model. So you want to keep documented all these, because if your iteration is not compliant with the tolerances and the errors, then you want to refer back to them and try to obtain spot measurements or log information trends from the energy management system and input them into your energy model. And also it's a way to reproduce the results, because a calibration I've read in the research is that there's so many ways to arrive to a calibration model. You can tune that, tune this, and if different models are given the same building to model, then they're going to arrive at different results. So that's where the data hierarchy comes in. It's they want to get evidence-based data adjusted instead of just tuning this or tuning that and just getting completely different results, but still arriving at the calibrated result. And a good way to just keep track of the changes is version control software. There's one open source one called Tortoise SVN. So it just tracks the changes of each of the IDS or the each of the data inputs for the software. So some of the logging equipment examples that Jake was going to talk about.
Excellent. I just want to mention one thing too about what Carlos was saying about documentation, and we kind of went back and forth on what the title of this presentation should be, and we toyed around with calling it, instead of just the art of energy model calibration, the dark art of energy model calibration, because it can sometimes be a very mystic, squishy, undocumented process. So the more that you can do of what Carlos was saying is the better in terms of QA, QC of your models, documenting the different iterations of calibration that you go through, and trying to make it as scientific as possible is just going to be better for you, better for the client, and better for anybody coming back to that model. Especially with how we work at the lab, we're working on multiple different models. Sometimes we're taking models that we've done in the past from someone else, and it can be really difficult to understand what is going on in a text file that's 10 megabytes or whatnot. So definitely important. In terms of some measurement and logging examples, it's been great having Carlos and Brad here to actually go out and use some of the equipment that we have available and that we actually can loan out to people doing energy efficiency studies because of Idaho Power through our tool loan program. It's on our website if anyone's interested. We're able to actually support our calibration efforts by using some of this logging and measurement equipment. So just a couple of examples that I wanted to point out. We've used lighting sensors to try to determine lighting schedules. This was Carlos's first model, but he had it easy. He had an energy management system where we could go in and find a lot of schedules and set points and equipment.
I had Mike as a resource.
Yeah, that's true.
Mike
building owner, and they've been fantastic in terms of the communication that we've been able to have with Manor Bank's management facility to help out. But other cases, smaller buildings that don't have that, you have to kind of get creative with even trying to figure out what is the lighting schedule. Hours of operation for an office don't always tell the full picture. Do they leave the lights on all night? You can do drive-bys at night. We usually will drop in a couple hobo lighting sensors. They're not very accurate in terms of like the lighting level, but they can pretty much tell you when the lights are on versus when they're off. And then we can go ahead and take some of that data and correlate a lighting schedule that we can then put into our models. That's one example. We did some pretty detailed temperature logging of an ERV one time to figure out what its effective efficiency was. I think it was like, 8 years old and it had some issues. So, whether that thing was 50% efficient versus 75% efficient, like the spec said, it made a pretty big difference in terms of what the overall energy was. So we, measured supply, temperature, return, outside air, and the exhaust, and we're able to come up with an efficiency equation that we then used for the model. Those were just simple hobo loggers. Airflow measurements for rooftop equipment is pretty tricky. We have, a flow plate, which we can use for small air handlers, and residential size buildings. But you can also do, we have different static pressure, don't know the technical term for it. It's essentially a tube that you put before and after the fan. You measure the static pressure difference, and you can actually come up with the CFM using the fan curve. So there's a lot of different ways that we can get airflow because that's something that's pretty variable as well. According to the model and how it uses energy. Also, we've done plant loop temperature logging. Sometimes the systems have probe ports. Sometimes you have to get a little bit creative with how you do that. But that's definitely an important one that we've done before. Economizer testing can be pretty big, making sure the set points works, just making sure everything's hooked up correctly. So that's something we've done in the past. We just did a combustion efficiency test for a boiler, which was great. We actually had to borrow some equipment from BSU's program, but we actually, I believe, got something this year to be able to do that in-house. And then we've also done some whole building pressurization tests now for 2 buildings where we've actually come up with a scientifically backed up number for the infiltration. Anyone who's done energy simulation knows that infiltration is a pretty big lever for calibration, and it's a huge question mark too. I mean, it can vary widely what the actual baseline infiltration is. So these tests are pretty critical in trying to quantify some of the specific characteristics of some of those buildings. So we did one on office building. We just recently did one on the hotel that we've been working on, and we use that number in our energy model. And then let's see, pump spot measurements with circuit transformers, and we've also done state loggers on cooling equipment to actually try to determine their cycling rates and stuff like that. So those are just some of the examples. If you have any questions, come talk to me afterwards, and also if you're curious about the type of equipment we can run out, you can talk with Brad or check out our website.
So like I mentioned before, your first iteration of the model is not going to probably going to be deemed calibrated right away. So like Jake mentioned, there's a lot of logging equipment that you can use. Calls to the building manager, and I found this really neat flowchart that by Raftery, Kino, and Aldano that just specifies the flowchart of trying to get more information. So is there a clear discrepancy source, or is it a modeling error? Like modeling errors can include a wrong weather file in the simulation, or days that are defining say time frames for the simulation model. And I've done that where when I want a annual simulation instead of and it's like the parameters are just to do 1 month. So gotta check out what the discrepancy is. Is it going to take a lot of resources to get that additional information? If not, just continue on, do the spot measurements, do the trend logging. If it is, a sensitivity analysis of the model can be useful if the parameter that you're trying to test, does it impact the energy, the final energy in the building enough to make a difference, or if not, just you can be done with the model. If it does, then get a new information from previous research or from logging equipment. So the next few slides is just the major steps in my calibrated model banner bank. So I'm just going to run through this because we're almost out of time. So the first one is just initial model. After I complete the whole build the geometry, did the thermal zoning, and define all the set points. And this is ideal load, so that's why we have a low. The dashed lines are simulated, and solid lines are actual energy consumption. For the red is electricity, and purple is gas consumption. So the reason why we have small or smaller electricity use is because in the first one I used ideal runs, ideal loads. It's not going to take any of the inefficiency of the equipment in the simulation model. So after I do that, so the target is 78 and my current is 111. So my infiltration assumptions were off initially, so I adjusted that to I cut them in half, so that reduced my gas consumption by quite a few percentages, about 30% of the gas consumption. So you can see it made a big difference there. So it reduced down the EUI by 30% to 73. So after I put the real system in, defined the real HVAC system of the building, you can see it took into account the inefficiency of the equipment, raised the electricity, but I'm still off by 400 in the simulated gas consumption, and 30% off in the simulated electricity consumption. So I adjusted some heating operations because in the one before I was getting gas consumption in the summer. Well, and obviously they don't use very much gas in the summer, so I adjusted the hours of operation of the boiler or the geothermal system because they don't have the boilers as backup in the building. So I adjusted that, brought down my energy consumption back to 82. Adjusted some supplier set points that reduced down again the total EOI. Did some minimum outdoor air requirements. I went from 30. It was defined to the default values of 30. So I brought him back after talking to the building manager. I brought him down to 20%. So that got my EOI 74%. As you can see, also I'm lower than my target, but the fuel splits are not the same. So this is where I'm talking about the fuel splits offsetting each other. So I have low electricity consumption but high gas consumption. So I added chiller resets in, but still the EOI didn't change. And again, it's because of the offset. This was raised up a little bit, and the gas consumption lower. So, and that's my where I left off. I'm still working on it, trying to get it calibrated. So my current, I performed the two methods of deeming the calibrated model. For the electricity, I'm 30% off on both criteria, and for the gas, it's a little bit higher, 75 for the coefficient of variance, and the mean bias error is about -%. I have a high gas consumption. So my assumptions in the for the building was infiltration. I assumed a number through a calculator, using a calculator, and then adjusted that number to reduce the heating. And then the major plug loads, we did a study for 2 of the floors in the building, and I assumed it to be the same for all the floor plans, so I might have to go revisit that and adjust it. Minimum fresh air requirements was a big thing, but now after talking to the building manager, I can cross that off now as a major assumption. And then I assume that the lighting energy management system to be accurate as it's diagrammed in the system. And so little things to go revisit if I can't make it work. Another thing that's going to bring up my electricity use, I haven't defined any of the dikins for the data center cooling requirements, so that's going to bring up my electricity use as well and for the simulation model. And some levers of calibration, as Jake mentioned, it was infiltration, ventilation requirements, and HVAC months of operation. That's a big things that can swing your simulated model one way or the other. Takeaway, it's an iterative process. HVAC systems can be hard to model, especially when it's custom setup. There's usually not templates in the simulation software to go off by. And you can simplify your model too much, but not simplify much as you can, but not too much where you don't have control over your simulation. So, any questions?
So with that, thank you, Carlos. We have time for some quick questions. If you need to leave, please go ahead. But first, fill out your education evaluation form. And then, yeah, we can just try to take a couple of questions before people take off.